Hi ladies and gentlemen, in this video we discuss ripple counters. This is one principal application of flip-flops. So let me start with that presentation. The speech is organized into your learning outcomes, then the theory of ripple counters, and then we will see the design of a 3-bit up and down counter. Then we will see an up down counter using mode control, then the summary of understanding. So what you will learn are you will learn the theory and design of frequency counters using flip-flops and realize them in QUCS and verilog. Then you learn the circuit of a 3-bit down counter as well as a 3-bit up-down counter. So ripple or asynchronous counters are formed by cascading T flip-flops because in the theory of T flip-flops you have seen that it toggles in every clock cycle for T equal to 1. So such toggle flip-flops are commonly used in ripple counters. So sometimes JK flip-flops are configured as T flip-flops. So in this cascade, if you can see this diagram, you can see that this is the first flip-flop. This is clocked by an external clock, and its J and K are connected to 1, that is T is equal to 1. So this output Q0 toggles every clock cycle. Now its output is connected to the clock of the next stage, and that toggles in every state change of this first Q bar, and the output here of the second flip flop, that is also connected to the clock input of the third flip flop. So that you get a pattern like Q2, Q1, Q0. Q0 toggles in every clock cycle. Q1 clocks in every other clock cycle, and Q2 will have a much less frequency, half of that frequency. So the succeeding flip-flops are triggered by outputs from the previous flip-flops. So this circuit is a 3-bit up counter. This is a 3-bit up counter. So these are leading edge triggered flip-flops. So if you are using a leading edge triggered flip-flop, if Q bar is connected to the next clock, then it will up count. That is, it will count in the sequence 0, 0, 0, 0, 0, 1, 0, 1, 0, etc. to 1, 1, 1, and then reset to 0, 0, 0. So the maximum count cycles in this are 8. That is 2 raised to 3. There are 3 flip-flops, so 8 clock cycles are counted before resetting. So if it is a leading edge triggered flip-flops, what I have to do is for up counting I have to connect Q bar to the next clock. Here also Q bar to the next clock. If it were a trailing edge triggered flip-flop, I would be connecting Q to the next clock for up counting. If for down counting, these are in the other way. That is, if it is a leading edge triggered flip flop, then I have to connect Q to clock for down counting, and for trailing edge triggered flip flops, I have to connect Q bar to the clock for down counting. So in this, this is an asynchronous circuit, meaning that only the first flip flop is connected to the external clock. All others are clocked by the previous Q output or Q bar output. So it looks as though the clock ripples through the cascade from the first to the last flip-flop, and that's why the name ripple counter. So here there is an active low reset initially. So this active low reset resets all flip-flops to 0, 0, 0. So when the first clock comes, Q0 is toggled. So Q0 becomes a 1, counting 0, 0, 1. Then at the next clock cycle, this Q1 is toggled, and Q0 toggles to 0. It becomes a 0, 1, 0, etc. Now this, whatever is given in blue, that should be understood thoroughly. Q output is connected to the clock input of the next stage in trailing edge flip-flops for up counting. If it is a Q bar is connected, then it is down counting. If it is a positive edge triggered flip-flop, Q bar output is connected to the next clock for up counting, and Q to clock for down counting. So let us see the QUCS simulation for this circuit. Here you can see that these are 3 T flip-flops connected with all T's connected to 1, and presets and clear are connected to high, so that normal operation is ensured. Here a clock, 1 nanosecond clock is applied to the first 10 nanosecond clock is applied to the first clock of the first flip-flop. Its output Q bar is connected to the next clock, and so on. Now if I run this simulation, you can see the counting cycles. Now you can see that here this is I will show you all the waveforms including Q bar. The clock is there, Q0 is there, Q0 bar is there, Q1 bar, and Q2. I'll make this Q2 more visible. Okay. Here you can see that there is a clock that is low for 10 nanosecond and high for 10 nanosecond. So the Q0 toggles this way. So this is a leading edge triggered flip-flop. So initially Q0 is 0. So it toggles to 1 at the first clock cycle and stays that way. Then at the next 13 nanosecond, this again toggles. It goes from 1 to 0. And it stays that way until it sees the next clock at 50 nanoseconds. So you can see that this Q0 has a frequency that is half of the clock. Okay, its time period is now 20 nanosecond. So while the clock has it has 40 nanosecond, while the clock has a 20 nanosecond period. Now Q0 bar is used to clock the next stage. So this is Q0 and this is Q0 bar. So Q1 changes state at every positive edge of Q0 bar. So initially Q1 is low and it stays that way. Here at when Q0 bar goes high, it switches to +1. Then here it again toggles to 0. And at 110 nanosecond again it toggles to high. Now Q1 bar, the Q1 bar is used to clock the third flip-flop. So this is my Q1 bar. So initially Q2 is low and it stays that way until it meets the positive edge of Q1 bar, that is here at 70 nanosecond it goes high. So you can see that if you look at these waveforms, I will remove this complemented waveform so that you can easily understand the counting cycles. I delete these graphs. So here you can see that initially the count is 0 0 0. Q2, if you look at Q2 Q1 Q0, it is 0 0 0. Then it at the next clock cycle it becomes a 0 0 1. Then it's a 0 1 0. Then 0 1 1 1 0 0 1 0 1 and 1 1 0. And finally 1 1 1 before resetting to 0 0 0. Again it becomes 0 0 0 here. Now you can observe the truth table also here. Here you can observe these counting cycles 0 0 0 0 0 1 0 1 0. So whenever the clock is high, next clock count occurs 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1, and it resets to 0 0 0. Okay, so this is how an up type ripple counter works. Now let us go back to my presentation. Now we can implement this in Verilog. We can have a 3-bit up counter with Verilog. Here what I do is I include the device JK edge. This is a positive edge triggered JK flip-flop. We have seen its development earlier when we discussed the flip-flops. Now I start a module called up counter, module up counter end module. Q bar JK outputs are Q and Q bar, which are 3-bit wires. okay, 0 to 2, 3-bit wires. Q and Q bar are 3-bit wires. Inputs clock, JK and K. Inputs are reset and preset, clear and preset. Then what I do is, otherwise I will show you the code here. Now here you can see this code. I include the JKFF positive edge triggered flip-flop, and I start a module up counter and end module. Here you can see that Q bar are the outputs and JK clock reset and preset are my inputs. So outputs Q and Q bar are 3-bit wires, and input are clock, JK and reset and preset. They are wires. Now I make 3 instances of this flip-flop to realize that ripple counter. So it is a JK pos edge. This is device in JKFF underscore edge. So this is some name JKFF0. Q0 is my output, Q bar is my output, Q bar 0, Q0 and Q bar 0. Then JK clock reset and preset. Here the external clock is applied to the first flip-flop. Now for the second flip-flop, this Q bar output is fed to the clock. So here second flip-flop is JKFF1. Q1, Q bar 1 are the outputs, JK are the inputs, then the clock is Q bar 0. That is the Q bar output of the first flip-flop is fed to the clock of this one. Then reset and preset. Then the third flip-flop, its outputs are Q2 and Q bar 2, JK, but the clock is Q bar 1 is the clock to the third flip-flop. So that way we end the module. Now we can have a test bench corresponding to this. Here you can see that this is the test bench. You include upcounter.v and you start a module test bench. Then inputs are declared as registers. JK, clock, clear and preset, they are declared as registers, and Q bar are wires, 3-bit wires. And I make an instance of the up counter, say some name C1, Q bar, JK, clock, clear and preset, and initial begin. You start the monitor just like we discussed in previous cases. Then I dump to the waveform file rippleup.vcd. The waveforms are dumped to a VCD file rippleup.vcd. Then I apply various inputs here. So we can run this simulation and we can observe the outputs. Okay. verilog. Upcounter.v. Now it is compiled without any error. So what I do is upcounter test1 is there. With some -o a dot out. So now it is compiled without an error, and an executable a dot out is created that I run with a dot out /a dot out. Now you can see that these counting cycles are available here. Initially at 0 nanosecond, you can see that the clear equal to 0. Initially it is cleared. Normally most systems have a power on reset. So whenever you turn on the power, everything is reset. A reset signal is given to everything. So that this is called a power on reset. At t equal to at 0 nanosecond, the clear is made 0. So output is reset to q equal to 0 0 0 and q bar is 1 1 1. At 5 nanosecond, you apply this clock equal to 0. So it stays that way. At 10 nanosecond, the clock is active and it counts to 0 0 1. Again at 15 nanosecond the clock is low, so it remains in 0 0 1. Again at 20 nanosecond the count becomes 0 1 0. Q bar is 1 0 1. Then 0 1 1 1 0 0. That way the count proceeds. 1 0 1 1 1 0. Okay, 1 0 1 1 1 0 and 1 1 1, then back to 0 0 0, and it restarts counting. So this is how you simulate a ripple counter, an up ripple counter with a positive edge triggered flip-flops in verilog. So let me go back to my presentation. What if I want a 3-bit down counter? All I have to do with a positive edge triggered flip-flop is to connect this Q to the clock. Okay, here the first flip-flop is triggered by the external clock, and the next next flip-flop is clocked from the Q of the previous stage. Here the Q of the previous stage is connected to the next clock. Okay, so this is how a 3-bit down counter works. Now we will see its simulation in QUCS. I can start. This is a down counter. Here you can see that the Q output is connected to the clock. So this way this works. So only changes from the previous circuit. Q, instead of connecting Q bar to the clock, we connect Q to the clock. So I run this simulation. You can see that the counting cycles are this way. Initially it's a 111. Initially it's a 000. First count is a 111. Then at next clock it counts 110. Then at the next clock cycle, clock equal to 1, it is 100, 101, 100, 011, 010. Then it is a 001. Then 000, 000, then it counts to 111. Okay, we will see the waveforms. The clock, Q0, Q1, or I will put the other way, Q0, Q1, Q2. So you can see that so this is how the clock comes. Clock is every 20 nanosecond. The clock has a period of 20 nanoseconds. And Q0 here initially it is 0. It was 0. So at the first clock it goes to high. It becomes a high and it stays there until 30 nanosecond. You can see that the frequency of Q0 is half that of the clock. Like every T flip-flop. So Q1 is triggered with Q0, the flip-flop 1 that is triggered with Q0. So it comes here, it becomes a high, here it becomes a low, here again at the positive clock it becomes a low. That way you can see that the frequency of Q1 is half that of Q0, and Q2, frequency of Q2, this clocks here and here at the positive edges. You can see that the frequency of Q2 is one half of that of Q1. So the counts are 000 initially because it is reset initially. Then it is 111, 110. Here it is 110, 101, 100. That way down to 000. Then it restarts from 111. So this is how I connect a ripple down counter. So for a down counter, if it's a if I'm using leading edge triggered flip flops, I have to connect Q to the next clock. If it is a trailing edge triggered flip flop, I have to connect Q bar to the next clock. So this being understood, let me go back to my presentation. Now then I can have an up-down counter using mode control. Or you can see a simulation in Verilog. I can have a verilog simulation also for a down counter. I have a ripple down. I have a down counter.v. And here I use a down counter. So the only difference is instead of connecting Q bar here at the clock, I connect Q0. Here I connect in the second flip-flop I connect Q0 in place of clock, and here in the third flip-flop I connect Q1 in the place of clock. So this is a test bench return for that. I have to include the down counter and make a module this way, a test bench this way. I apply these clocks. We can see this operation. I can run down counter.v. Now it is simulated without any problem. So then it is a test, then minus O a dot out. Oh, I think the name is different. I think it is a down counter test dot v. Okay, now it is compiled without any error, so I can run this a dot out and see the down counting cycles. Now you can see that here at 0 nanosecond Q is reset. So at first clock, that is here at 10 nanosecond, the first clock comes, the count goes to 111. Then at the next clock equal to 1, it is 110. Then 1001, 100, 011, 010. That way it down counts. It down counts from 7 down to 0. Here Q equal to 0, again it presets to 111. After 000 it counts 111. So this is how the ripple down counter behaves. Now you can observe these waveforms. I have a dump. What is the file I have written here? It's a ripple down.vcd. I can say here ripple down.vcd. I can open this with GTK wave. You can see these waveforms. I can see the clock, Q and Q bar. I can add here. I can append a clock. I can append Q bar. You can see these counting cycles. You can see this counting cycle. Q counts initially it is 000, then 111, 110, 101, 100, 112. You can say down to 000. Then it starts counting 111, 110, etc. This is just a complement of that. Q bar is a complement. If Q is up, when Q down counts, Q bar up counts. It is initially 111, 000, 1010, etc. When Q bar up counts, when Q up counts, Q bar down counts. When Q down counts, Q bar up counts. So this is how the waveform looks like. These are the clock cycles. Now you can say this presentation again. Now I can make a counter that counts up and down based on a control signal. So what we know is this being a leading edge circuit, if Q bar is passed to the clock, then it up counts, and if Q is passed, it down counts. So I can use a controlled inverter to pass either Q or Q bar to the next clock. So I can easily make a controlled inverter with an XOR gate. So if so this a Q output of the first stage is connected to an XOR, and the other input is connected to a mode control. Okay, here also the Q1 is connected to the clock of Q2 through a controlled inverter with XOR gate. So one input of which is connected to the mode. So if this mode control is a 1, then Q bar appears at the clock. If this mode control is a 0, what will happen? Q appears at the clock. So if mode control is a 0, then if it is a 1, it up counts. If it is a 1, it up counts, and if it's a 0, it down counts. Because if it is a 1, if the mode is a 1, Q bar appears here. So this being a leading edge triggered flip flop, if Q bar is connected to the clock, it up counts. And when the mode is 0, Q appears at the output, then it down counts. So you can see a simulation of this circuit in QUCS. Here you can see that this is a mode control thing. These flip-flop outputs are connected to clock through an XOR gate, which is a controlled inverter. So if this control bit is a 1, Q bar goes to the clock. If this control bit is a 0, Q goes to the clock. So this here this control line is put as a signal. So I can simulate this circuit and see the counting cycle. So here you can see that here you can see these waveforms. Here initially the control is low from here to say 160 nanosecond. From 0 to 160 nanosecond the control is low. So if it is a 0, Q is passed on to the output. So what it does is a down counting. You can see that the counting cycles are 111, 110, 101, 100, 011, 0 that way. Now here at 160 nanosecond, what happened is the control goes high, so it starts up counting. Here you can see that here the count is 110. It is 110. When this control goes high, this last count was a 110. So before that it was a 110. So next will be a 111. Then becomes a 000, 001, 010. So from here, the 0 to 160 nanosecond, the circuit down counts, and from 160 nanosecond onwards, the circuit down counts. You can see the waveforms. You can see the truth table also. This is my clock, and this is my Q2, Q1, Q0, and you can see the control input also. Here while the control input is low, you can see that it's down counting 111, 110. You have to look at this clock equal to 1, that is 110, 110, 101 that way. And here what happens is it starts up counting from this is 011, then 111, okay, then 0. This clock is a 1 here. It's a 110, then 111, then 000. It starts up counting from there onwards. It is up counting 001. Here it is a 110, 111. You can see that it's 000, 001, 010, etc. So from here to here, this point it is down counting, and from here to here it is up counting. So you can make a single circuit work as an up or down counter based on the control input. What I use is a controlled inverter with the XOR gate, or you can use a 2:1 multiplexer here, but an XOR is easier. So you can make an up-down counter with 3-bit up-down counter with a verilog. I will show you that code rather than this. Here you have an up counter, up-down counter is there. I have up-down counter here. You can have an up-down counter here. You can have a test bench here. Okay, so you have this up-down counter. What I need is I need an XOR to do this. Okay, I use an XOR to as a control input. So everything else is the same. Only thing is instead of passing Q0 directly to the next clock, what I do is I make I XOR this Q0 with the mode control and generate A is given to the clock. Okay, then Q1 is XORed with a mode to get B, and B is passed on to the third flip-flop. So you can open a terminal and I can say I verilog counter.v and up-down test. I can say up-down test.v minus o a dot out. So you can see that dot slash a dot out. We can see the different counting cycles. If the mode equal to 1, if the mode equal to 0, what happens is it does down counting, 111110, that way it comes if mode equal to 0. If mode equal to 1, it starts up counting 100 101 110 111 000, that way. Then again, when the mode goes to 0, it down counts 110 101 100, etc. Okay, so this is how I simulate an up-down counter using verilog. So all the what I have made as a change is, the only change here is, instead of passing the clock, the Q bar output to the next clock, what I do is I XOR this Q bar output Q0 with the mode control, and this generates A output. This is an XOR gate, just the realization of that circuit. This A is applied to the clock input of the second flip-flop. Then this mode and Q1 are XOR to get B, and this B is given to the third to the clock of the third flip-flop. Okay, so this way you understand an up-down counter. You can see those waveforms also. Here the file is ripple updown.vcd. I can say this is my ripple down, then I have a ripple updown.vcd. You can take here, the test bench is there, you can apply this clock. Mode is there. Here the mode is low. From here to here the mode is low, so it is down counting, it is up counting, Q is up counting 0 0 0 0 0 1 0 1 0 0 1 1, etc. Here what happens is it starts down counting 0 0 0 1 0 1 0 0 1 0 0 0 1 1 1 1 1 1 0, etc. So here again it starts up counting. Okay, so this is how you verify this operation with verify the operation of an up-down ripple counter with the verilog. Now finally, coming to the summary of understanding, you learned the theory of ripple counters. So you understood how I make an up counter and a down counter. It is based on which type of triggering you have, whether you are using a leading edge triggered or trailing edge triggered flip-flop. If it is a leading edge triggered flip-flop, Q bar should be connected to the next clock for up counting, and Q should be connected to the clock for down counting, Q of the clock of the next stage. And if it is a trailing edge triggered flip-flop, for up counting I have to connect to Q of the previous stage to the clock of the next stage. If you connect Q bar to the next clock, then it down counts. Now you learned the circuit of a 3-bit up counter using T flip-flops, and you simulated it in QUCS and verilog. Then you learned down counter and simulated in QUCS. Then you learned up-down counter with a mode control, and you use a controlled inverter to work the same counter as up counter and down counter, and you simulated it in QUCS and verilog. And that is the end of this presentation. I thank you all.